Hello and welcome to my channel Crisp ML. This is Parijat. Today we will see how gradients are calculated when we use an activation function like ReLu. So in the previous video we have already seen how gradients are calculated for a single neuron when we use the mean absolute error loss and the mean squared error loss. So essentially ReLu is defined as the maximum of the input and 0. So essentially it is 0 when the input x is less than 0, and it is the input itself when the input is greater than or equal to 0. So essentially what it does is it filters out all the negative numbers and marks them as 0, and from 0 onwards it is whatever is the input, the ReLu function will take that as the output. So this is how the graph looks like. Now you may be wondering why we use such a function. So this is essentially, if you see, it introduces non-linearity into the output of every neuron. So it's or otherwise the neuron, as we have discussed earlier, will become a plain simple matrix calculation of linear outcomes if there is no activation function used. So if we are using multiple layers with multiple neurons, the outcome will be essentially a matrix multiplication of all the inputs fed into the neuron, and the neural network in itself will have limited capabilities to learn anything beyond linear functions. So using activation functions is what brings the element of non-linearity and the ability of a neural network to learn non-linear complex functions as well. Now in terms of activation functions, earlier to the introduction of ReLu, there were other activation functions used like sigmoid or tanh, but they are fairly complex to compute and very computation intensive and very time consuming. As opposed to that, ReLu requires very few computations. You can see here it's just essentially a filter rather than any computation at the time of activation. So it is widely preferred now in the to speed up the calculations. The example we will use is the same which we have used in the past videos. So we will take the logarithmic function. Our y actual value will be the input of the input x values. We will feed some values like 1 to 20, and the outcome will be the logarithm of those values. And we will use a single neuron. There will be one input, there will be one weight, one bias. So our outcome will initially be the multiplication of weight into that input plus the bias term and the function ReLu applied over that. So our goal will be, of course, to estimate the weight and the bias. The loss function, as usual, will be the mean squared error. We have already seen it performs better than mean absolute error. Alright, so updating weights, the formula will remain the same. The weight we are using here, stochastic gradient descent method, so the formula will remain the same. E will be our loss function, and we will update the weights with this formula, and bias with this formula. So some math before we proceed. Now here is where the difference starts to come. So instead of the output of the neuron, which we have earlier seen as Wx plus b, it will be the intermediate output, which we will denote with y1. And if we denote ReLu function by f, our actual outcome will be y equal to function of y1, which is nothing but the ReLu function applied over y1. And finally, the loss function will remain the same. It is essentially y minus y actual, the whole square. Okay, this is as per the torch implementation formula. Now, to find the gradient of the loss function with respect to weight and bias, we will again use the chain rule. So earlier it used to have two components, the partial differential of the loss with respect to y and the partial differential of y with respect to w, but here we will have three components. We will have the partial differential of the loss function with respect to y, then we will have the partial differential of the loss of y with respect to y1, and then we will have the partial differential of y1 with respect to w, and similarly the only part different for b will be the partial differential of y with respect to b. This formula we have already seen in the previous video. It's a simple partial differential of the loss function with respect to y, and here it's is the formula where it changes. So we have seen y is equal to the ReLu function applied over y1. Now how do we compute the gradient for this? Now we already know that when y is equal to 0, it's essentially when y1 is less than 0, then we will define y as 0. So it is essentially a constant. So the gradient will nothing be but the partial differential of y with respect to y1, which will be nothing but 0. And when we say that y is equal to y1, when y is greater than or equal to 0, so essentially again, if you see, if you take the partial differential of both the sides with respect to y1 here, you will get that is equal to 1. So if you see, the last part again is same, which we have seen in the earlier video. Y1 is wx plus b, and the partial differential of y1 with respect to w will be x, as b will be treated as constant, and similarly for partial differential of y1 with respect to b will just be 1, as the other terms will be treated as constant. So putting it all together, we had this formula. So all the three components, if we take, we will have this. All these three components will be there. This is the part which is new, which is the partial differential of the ReLu function. Okay. Similarly for B, all the three parts will be like this. Alright, now let's look at some sample code and a simulation in a spreadsheet. Alright, so let's start with the simulation here. So we will have our epoch, we will have the input x, then we will have the y actual value, or let's keep that for later. So we will have w, we will have b, then we will have y1, which will be wx plus b, then we will have y, which is ReLu of y1, we will have the y actual, which is the log value of the input, and then we will have the loss function, which is this minus y actual whole square. Then we will have the partial differential of the loss function with respect to the final outcome, that is y. Then the partial differential of y with respect to y1. I have used the dollar sign here. You can use any sign. I've just used the dollar sign for convenience. Then we will have the partial differential of y1 with respect to w, and same thing for with respect to b. Alright, so then we will have the final gradient for calculation for w and for b, and then we will also have the learning rate, okay, which we will initialize to 0.001 for now. We have seen this value is a good starting point. Now for epoch, we are in one epoch, and as we have discussed earlier, we will be feeding one data point at a time for ease of simulation, for ease of discussion, and for ease of calculation. Okay, so in first epoch we will have values from 1 to 20, and we'll just see how gradient calculation works for that. So over previous examples we have seen, we start at these values of w and b. We have found, so over multiple iterations, these are good starting points, but then again I will encourage you, you can try it out with other values and let me know in the comment section below how does it perform. Alright, so we have w and b, so y will be nothing but w times the input plus b, then this y1, so y, so here is the formula for ReLu. So if y1 is less than 0, it is 0, otherwise it is the input itself. Y actual will be the natural logarithm of the input, and the error will be nothing but y actual whole square partial partial differential with respect to y will be 2 times y minus y actual. This will be again, so if y1 is less than 0, it will be 0, otherwise it will be 1. This will be again x, and this will be again just 1. Okay, and this will be, as per the chain rule, this will be the formula to this multiplied by partial differential with respect to y1 and then partial differential with respect to y1 with respect to w. So the formula will be here, and similar for b. Okay, so now let's see the step size and the gradient up, and the update for weights and bias will be nothing but we will take, as per the formula, the weight minus the partial differential of the loss function with respect to weight times the learning rate, and similarly for b it will be b minus the partial differential of the loss function with respect to b times the learning rate. And here we go, and the rest are of course formulas as we get. Okay, and here we see the outcome getting updated, and now we can just drag them down. And this is what we get. So if you would have noted, just like in previous example, we have been feeding data in batches of 1 data point at a time, which is for our convenience of discussion, for tracking the calculations, for matching with the simulation that we will see in the code. So this is what we get. So the error function, if you see, will be like this. So this is essentially very similar to what we have got. Of course, we have just done one epoch with one neuron, and so it's kind of converging, but it's very similar to what we have used without ReLu. And let's see what is the average epoch loss here. So first let's take this sum. So technically epoch loss is the average value which we take. So it is 0.7765, which is slightly higher than the earlier examples that we have seen, but then again, as I said, this exercise is more to demonstrate the effect of ReLu rather than compare between the methods, and this is almost practically the same value. Alright, so let's run it for 2 epochs and see if what are the values coming out for the second epoch. So if we just essentially copy this here, we can just put this as the second epoch. This will be nothing but the formula which we are seeking here. One second. Okay, so sorry, this will be, we'll have to drag it down. All these are formulas, so we'll have to drag it down. So alright, so here you can see the epoch loss has reduced from 0.7765 to 0.5088. So we are seeing some improvement. Alright, so we have written here the code for a similar simulation in PyTorch. I'll briefly explain it. So we're importing the libraries, and then for 1 to 20 we are creating a data point so that we have an array of tuples. So I will show you how this looks like. If you run this, please note why we are doing this is, so as you can see here, it looks like this. So this is an array of input values, and if you look at y, so this is an array of output values. Okay, so why we have done this is, we will be using the data loader class, which will be feeding one input data point at a time. So in order to match with our Excel simulation, so now we will define the tensor data set for x and y from this NumPy arrays, and then we'll just print a sample value. So this is for x and this is the y values for those. Okay, all right, so we will import the data loader class. We'll define our batch size as 1, and from the data loader class, which essentially loads the data from the given data set like just we saw, we are defining the data loader on our data set, which we defined here for x and y. The batch size is 1, and we have kept shuffle equal to false. If you keep shuffle equal to true, it will randomly pick up the values without replacement from the data set. But for our sake of discussion, again I'll repeat that we have to match it with the Excel simulation. So we have feeding one data point at a time, and in the strictly in the order from 1 to 20. So we have kept shuffle equal to false, and then it will follow this model. So now for defining the model, it is simply one neuron, and which has one input and one output, and after that it goes into the ReLu activation. So overall the model is nn.sequential, which has one neuron, and after that the activation function. So let's define that as well. So again, as we have discussed and as we have seen in the earlier videos also, we are initializing our weight parameter for the neuron as 0.1455 and the bias to this value. For this, we will access the neuron value for nn.linear, the neuron value for model of 0 with the subscript of 0. That's the first layer, and the weight and the bias. Okay. So now our criterion is MSE loss and our model is SGD. We have kept stochastic gradient descent because it will match exactly with the formula that we have seen in the spreadsheet. Now going forward, we will also be explaining how different models work, how SGD can be used with different variants, but for now we will just stick with SGD. Okay, so here we'll keep number of epochs as 1. This is the outer loop for running the number of iterating over different epochs. We will initialize a counter here, and we will also initialize a variable for adding up the loss for each data point during the epoch. This is the value which we will divide by the counter, which will also get updated during each run of the data point, and this will help us in calculating the average epoch loss in the end of each epoch. So now we will load the data points using the train loader. Train loader, if you remember, is nothing but the object of the class data loader, where we have initialized the batch size to 1 and shuffle equal to false, so that we load the data points exactly in the order of 1 to 20 so as to match our spreadsheet calculation. And then we will print the model weight and the model bias. We've already seen how to access them using the subscript of 0. Then we will make the prediction calculation, and then the optimizer will set all the variables attached to it to 0 gradient. So basically the variable is nothing but the model dot parameters, and here effectively it is a single neuron which has the gradient attached, so it will initialize it to 0. Then we will calculate the loss using the criterion, which is nothing but the MSE loss, and after that this is the step which will do the gradient calculation. Once this gradient calculation is done, we will run the optimizer dot step, which will use the gradients calculated for each of the parameters, that is weight and bias, in this step, and it will use them and the learning rate to update the weight and bias. So these two calculations is the one which should match, and then of course we'll update the epoch loss total sum in each run of the data point. After that, for each of the data points, we'll print the X and Y, we'll print the prediction, we'll print the loss. We will also print the gradients calculated for weight and bias, and then we'll update this counter. Now at the end of each epoch, we will print the average epoch loss, which will be the sum divided by the counter that we have updated. Okay, so now let's run this. Alright, so as a quick check, if you see the epoch loss is coming out to be 0.77656, which if you see exactly matches with this value, and hence overall more or less we are correct. Other decimals may be a rounding effect, but let's check out few of the iterations. Let's just look at the last data point. So if that matches, overall our calculations are correct. So let's look at that here. So if we see here, it is 0.1971 is the weight, which is exactly matching 0.197077. So this is the rounding which we can do here, and then the bias is 7287. That is also exactly matching. The loss value is 0.044714. That is also exactly matching here, and the gradient values are nothing but 8.684 for the weight and 0.434, so they are also exactly matching here. Alright, now let's see what happens when we run this for 2 epochs. So we'll just make number of epochs equal to 2, and then we will run this complete thing. Alright, so at the end of the second epoch, we are seeing the value is exactly matching with the epoch loss. So 0.5088 is what we are getting here, and that is exactly matching. So we are able to now work it out for ReLu. We have successfully worked out the gradient calculation for ReLu. Thanks for watching this video. I hope you liked it. Please do let us know about your thoughts in the comment section below. In the upcoming videos, as we discussed earlier, we will be planning on introducing how we calculate the gradients for batches, how different optimization functions like gradient descent, Adam, etc. work, and we will design a simple dense network. So stay tuned and thank you.